How to implement the Softmax function in Python. From the Udacity's deep learning class, the softmax of y_i is simply the exponential divided by the sum of exponential of the whole y vector, where sy_i is the softmax function of y_i and e is the exponential and j is the no of columns in the input vector y. I've tried the following. Which returns. But the suggested solution was which produces the same output as the first implementation, even though the first implementation explicitly takes the difference of each column and the max and then divides by the sum. Can someone show mathematically why? Is one correct and the other one wrong? Are the implementations similar in terms of code and time complexity? Which is more efficient?
They're both correct, but yours is preferred from the point of view of numerical stability. You start with by using the fact that a b, c, equals a to the power of b, a to the power of c, we have, which is what the other answer says. You could replace max x with any variable and it would cancel out.
Well, much confusion here, both in the question and in the answers. To start with, the two solutions, i.e. yours and the suggested one, are not equivalent. They happen to be equivalent only for the special case of 1D score arrays. You would have discovered it if you had tried also the 2D score array in the Udacity quiz provided example. Results-wise, the only actual difference between the two solutions is the axis equals the 0 argument. To see that this is the case, let's try your solution, your underscore softmax, and one where the only difference is the axis argument. As I said, for a 1D score array, the results are indeed identical. Nevertheless, here are the results for the 2D score array given in the Udacity quiz as a test example. The results are different. The second one is indeed identical with the one expected in the Udacity quiz, where all columns indeed sum to 1, which is not the case with the first, wrong, result. So, all the fuss was actually for an implementation detail, the axis argument. According to the numpy.sum documentation, the default, axis equals none, will sum all of the elements of the input array. While here we want to sum row-wise, hence axis equals 0. For a 1D array, the sum of the only row and the sum of all the elements happen to be identical, hence your identical results in that case. The axis issue aside, your implementation, i.e. your choice to subtract the max first, is actually better than the suggested solution. In fact, it is the recommended way of implementing the softmax function. See here for the justification, numeric stability, also pointed out by some other answers here.
So, this is really a comment to DessertNut's answer, but I can't comment on it yet due to my reputation. As he pointed out, your version is only correct if your input consists of a single sample. If your input consists of several samples, it is wrong. However, DessertNut's solution is also wrong. The problem is that once he takes a one-dimensional input and then he takes a two-dimensional input. Let me show this to you. Let's take dessert nuts example. This is the output. You can see that dessert nuts version would fail in this situation. It would not if the input was just one-dimensional like np.array1, 2, 3, 6. Let's now use 3 samples since that's the reason why we use a 2-dimensional input. The following x2 is not the same as the one from dessert nuts example. This input consists of a batch with 3 samples. But sample 1 and 3 are essentially the same. We now expect 3 rows of Softmax activations where the first should be the same as the third and also the same as our activation of x1. I hope you can see that this is only the case with my solution. Additionally, here is the results of TensorFlow's Softmax implementation. And the result.
I would say that while both are correct mathematically, implementation-wise, first one is better. When computing softmax, the intermediate values may become very large. Dividing two large numbers can be numerically unstable. These notes, from Stanford, mention a normalization trick, which is essentially what you are doing.
If you want to see more, please consider subscribing.